This is video 25.5. We're looking at electrical potential energy. And this is closely related to electric potential, but this is energy, and it's a concept we're familiar with. The potential energy of a system of charges is defined to be the work required to bring them from infinity to their locations. So let's say we want to find the electric potential energy of a two-charge system. So we'll say we've got Q1 and Q2, and they're a distance r apart. So what we have to do is first bring Q1, and then bring Q2 in from infinity. Now the work required to bring Q1 in from infinity is 0. Because there's no other charges there. There's no forces that act on Q1 as we move it, so we don't have to do any work. Basically because Q2 isn't there yet. And that tells us one very interesting thing, and that is that the electric potential energy of an isolated charge is a meaningless concept. Now the amount of work required to bring Q2 in from infinity is equal to Q2 times the change in potential we move it through. So we're moving Q2 from 0 potential at infinity out up to non-zero potential near Q1. And so this delta V here is the potential due to Q1. And that works out to be KQ1 Q2 over R is the electric potential energy of two charges. This will be positive if the charges have the same sign. It will be negative if the charges have opposite signs. We'll look more about what the sign of that energy means in a bit. But you should memorize this equation, know that it applies to a system of 2-point charges. Now if you have a system of 2 or more charges, let's say that we have Q1, Q2, and Q3, and we'll say that the distances between them are R12, R13, and R23. The work required to bring Q1 in from infinity is 0. The work required for Q2 is KQ1 Q2 over R12. That's what we derived on the previous slide. But now let's see what happens when we add a third charge. If we're bringing Q3 in, the work that we have to do is equal to Q3 times the change in potential. But that change in potential is now due to both Q1 and Q2. So delta V is equal to KQ1 over R13, so the distance to Q1, plus KQ2 over R23, which is the distance to Q2. And so that means the work for Q3 is KQ1 Q3 over R13 plus KQ2 Q3 over R23. And we notice that the total energy of the system is KQ1 Q2 over R12 plus KQ1 Q3 over R13 plus KQ2 Q3 over R23. For 3 charges, you have 3 two-particle interactions. You have the interaction between 1 and 2, the interaction between 2 and 3, and the interaction between 1 and 3. So essentially, you're adding the potential energies associated with each of those 2 charge interactions. If you add a 4th charge, you have now increased the number of interactions to 6, and you have 6 terms in this. If you have 5 charges, you increase the number to 10, If you have 100 charges, you have something close to 5,000 interactions. So this gets very complicated very quickly. But you're probably not going to be asked to find the energy of more than 4 charges. So it's really not that bad. Just remember that you have to find the interaction of every pair of charges. Now, an example of how you'd use this, you've got 2 electrons that are fixed 2 centimeters apart. So here's an electron, here's another electron, that's 2 centimeters. We're taking a third electron, we're shooting it in from infinity. So it starts out with some velocity, and it has exactly the right speed that it stops halfway between the first 2. Question is, what was that initial speed? Now this is a conservation of energy problem. The idea is that the change in the kinetic energy, so when it gets here to the end, kinetic energy is 0. At the beginning, kinetic energy is 1/2 mv squared, where m is the mass of that electron. And so the initial kinetic energy plus the initial potential energy equals the final potential energy plus the final kinetic energy. Now this one equals 0, and that tells us that the initial kinetic energy, Ki, equals the change in the potential energy. So 1/2 mv squared is Ki. The change in the potential energy is the charge on the electron times the change in its potential. Now, the change in potential is just, the initial potential is 0. The final potential is that's going to be this interaction energy plus this interaction energy. So K times Q over 1 centimeter. And we'll multiply that all by 2 because there's 2 electrons up there. And you have this energy and this energy. And if we solve for V, doing a bunch of algebra, we end up with the square root of 4k q squared, where q is the charge on the electron, divided by mr, where r is 1 centimeter. If you plug in the numbers, you end up with 318 meters per second as the required speed for the electron just to stop right between the other 2 and then hang out. That's, of course, very unstable equilibrium. Basically, it's just a conservation of energy problem, but with electric potential energy. And now we have to ask, what does the sign of the energy mean? Now, I told you at the first slide, the beginning of the video, that if the charges have the same sign, the energy is greater than 0. And if they have opposite signs, the energy is less than 0. Now, we should also note that when charges have the same sign, you have a repulsive force. And when charges have opposite signs, you have an attractive force. And so we'll see that the sign of the energy is related to whether the charge is attractive or repulsive. Positive energies are associated with repulsive force. Negative energies are associated with attractive forces. Also, when you have a negative total energy, that's what we call a bound system. Just like with gravity. For an orbit, the total energy is negative because the system is bound. If the total energy of an orbit was positive, it's an unbound orbit and the planet will escape to infinity. Same thing here. And this analogy between gravity and the electric force is part of the Rutherford model of the atom, where electrons orbit the nucleus like planets orbit the sun. Tomorrow, I'm going to check questions 8 through 10. It deals with electric potential energy. and the next video will look at how energy and potential relate to conductors.